Right now, sunlight is landing on your skin. It left the sun 8 minutes ago, so you are already looking at the past. Now go further. The light from a distant star crossed the whole universe for billions of years to reach your eye. And here is the shock. That light did not age a single second on the way. For the light itself, 0 time passed. It was born and it arrived in the very same instant. Tonight we chase a beam faster than any rocket, freeze a ticking clock until it stops dead, hunt the oldest glow left over from the birth of everything, and stand at the rim of a black hole where light circles forever, unable to escape. If this bends your brain, hit like and subscribe and ride along. Take a breath. We begin. Step outside on a clear morning, and the warmth spreading across your face is a message that left home 8 minutes ago. The sun sits about 93 million miles away. That is a hard number to feel, so picture this. If you could drive a car to the sun at highway speed and never stop for gas or sleep, the trip would swallow more than 170 years. Light makes the same crossing in roughly 8 minutes. It is the fastest thing that exists, and even it needs those minutes to reach you. So the sunlight touching your skin right now left the surface of the sun before you started reading this. You are feeling the past. Warm, bright, ordinary past. Now, for the part that unsettles people, you never see the sun the way it is at this exact second. You only ever see it the way it looked 8 minutes back. If the sun somehow switched off completely, you would keep basking in golden light, hearing birds, squinting at a blue sky, with no clue anything had changed. The darkness would take a full 8 minutes to arrive. For 480 seconds, you would be living inside a sun that no longer existed. That gap between what is happening and what you see comes straight from the nature of light itself. Light is quick, close to unimaginably quick, yet its speed has a ceiling. Every beam carries a tiny delay baked in, a travel time between the thing that glows and the eye that catches the glow. For the sun, that delay is 8 minutes. For closer things, it shrinks. The moon hangs a little over 1 light second away, so the moon you gaze at tonight is a bit more than a second old. When Mars swings near, its rusty light reaches you several minutes late, a small red postcard mailed from earlier in the evening. Every time you look up, you are looking back. Think of light like a courier carrying a sealed letter. The letter describes exactly how the sender looked the moment it was closed. The farther the courier has to run, the older the news inside when it finally lands in your hands. A snapshot, delivered late, forever describing a moment that has already slipped away. Close to home, the delay is small and easy to shrug off. A second here, a few minutes there. Your brain treats the sky as a live feed, and for daily life that works just fine. The universe, though, is enormous, far larger than the cozy gap between us and the Sunday stretch that couriers run across the black ocean between stars, and the delay stops being minutes. It becomes years, then centuries, then a span so long it dwarfs all of human history. Here sits the quiet miracle at the center of everything we are about to explore. That old light, no matter how long it has been running, shows up sharp and clear, carrying its message perfectly intact. It arrives fresh. It reads as crisp as the day it left, even after a journey that would exhaust anything else in creation. To see just how deep into the past a single glance can reach, we only have to wait for the sun to set and the real time machine to switch on overhead. When the sun finally drops and the first stars prick through the dark, your view stops reaching back minutes and starts reaching back years. The closest star system to ours sits so far away that its light spends more than 4 years crossing the gap. So, the twinkle you catch from it tonight left home about 4 years ago. A kid who was in 4th grade when that light departed is finishing 8th grade by the time it lands in your eye. 4 years of school, packed into the flight of a single sunbeam from the nearest neighbor we have. And that is the close one. Look toward the winter hunter in the sky and find the bright reddish star marking his shoulder. That glow has been traveling for hundreds of years. It set out toward Earth back when people rode horses everywhere and no one had ever seen a light bulb. The star pumped out that light. The light began its long crawl across space, and only now, centuries later, does it slip into your eye on a cold night. Escalate that thought and it gets eerie. Some of those bright shoulder stars are old and unstable, the kind that can blow themselves apart. It is entirely possible that one of them already exploded, snuffed itself out completely, and we simply have not received the news yet. The light showing us a calm, glowing star could be an ancient recording of something that is already gone. We would keep seeing the ghost until the last of its old light finished the trip. So the night sky is a strange collage. Every point of light is a different age. One dot is 4 years old. Another is 400. Another might be 4,000. Your eye blends them all onto one flat black canvas, and your brain calls it tonight sky, when really it is thousands of separate moments from thousands of separate years, all delivered to the same address at once. Picture a wall covered in old photographs. One was taken last spring. One is from your grandparents' wedding. One is so faded it shows people no one alive remembers. You stand in the room and take them all in with a single sweep of your eyes, even though each froze a completely different year. The night sky works the same way, except the photographs are stars, and the wall is the whole universe. There is something almost tender about it. The light does not care how long the road was. It carries the exact color, the exact brightness, the exact fingerprint of the star that made it, and it hands that fingerprint over intact after a voyage no human mind can truly picture. That is the puzzle worth chewing on. A courier that ran for 4,000 years should be worn out, its letter smudged and torn, yet starlight arrives pristine. Astronomers can read the chemistry of a star from that ancient beam as easily as reading a label, pulling apart its colors to learn what it is made of, how hot it burns, how fast it moves. None of that would be possible if light aged, faded, or smeared on the long haul. The whole science of the sky leans on light, staying perfect across impossible distances. To understand how it manages that, we have to stop treating light as instant and start asking exactly how fast this courier really runs. Light moves so fast that our everyday words for speed fall apart trying to keep up with it. Here is a way to feel it. In the time it takes you to snap your fingers, a beam of light could race all the way around the entire planet about 7.5 times. One snap, 7.5 laps of the whole Earth. Coastlines, oceans, mountains, deserts, all of it circled again and again before your fingers finish the motion. Nothing you have ever seen comes close. A rifle bullet crawls by comparison. A jet is basically standing still. Even the fastest spacecraft humans have ever launched would look frozen next to a beam of light, like a snail parked beside a race car. Stretch that speed across the solar system, and the numbers grow, but so does the majesty. A beam leaving Earth would reach the giant planet Jupiter, way out past the asteroids, in well under an hour. Keep going, out past the last major planet, out toward the cold and lonely edge of the Sun's family, and the same beam needs several hours to get there. Fast as it is, space is so vast that even light starts to feel the distance. This speed has a special place in the universe. It is not just quick, it is the top speed, the hard ceiling, the fastest that anything is allowed to move. Nothing that carries weight, nothing made of solid stuff, can ever match it or beat it. Physicists have tested this over and over, in labs, in giant machines that fling particles as hard as they possibly can, and the wall always holds. You can push a particle closer and closer to light speed, pouring in more and more power, and it edges nearer, yet it never quite touches the line. Think of it like a speed limit sign, posted on every road in existence, one that the universe enforces without a single exception. You can drive right up to the limit, you can hug it, you can never cross it. That raises an obvious question. Why? Why should reality bother with a top speed at all? Why can a beam of light zip along at this one exact pace while everything heavier falls short, no matter how hard it strains? The answer turns out to be one of the deepest facts we know about the world, and it took one of the sharpest minds in history to crack it open. For most of us, a speed limit sounds simple. Go slower than the limit and you obey it. Go faster and you break it. Cars do it all the time. Surely, if you just built a powerful enough engine, you could shove any object right through that ceiling and out the other side. The universe says no. And the reason it says no has nothing to do with weak engines or missing fuel. It has to do with something woven into the fabric of space and time, something that only reveals itself when you try the one experiment that sounds easiest of all. That experiment is simple to imagine. Take the fastest ship you can dream up, aim it at a beam of light, and give chase. Common sense whispers that you should be able to catch up, or at least close the gap. What actually happens when you try breaks common sense in half? Picture yourself strapped into the fastest ship ever built, flooring the throttle in a desperate race to catch a single beam of light. Everything you know about chasing says this should work. Watch two cars on a highway, both cruising at 70 miles an hour side by side. To a driver in one car, the other car barely seems to move. It just hangs there in the next lane, matched and steady. The faster you both go, the slower the gap between you seems to change. Chase anything fast enough, and it appears to slow down relative to you. So racing after light, the beam should start to look sluggish. As your ship climbs toward tremendous speed, the light ahead should seem to crawl, until you are nearly close enough to reach out and touch it. Light refuses to play along. No matter how fast your ship flies, the beam ahead always races away at the exact same speed it had when you were sitting still. Crawl along slowly, and light leaves you at its full pace. Scream forward at nearly its own speed, and it still leaves you at that identical, unchanged pace. You gain nothing. The beam pulls away just as fast as it ever did, as if your enormous effort meant nothing at all. This makes no sense by highway logic. On the highway, closing speed adds up. Here, it simply does not. Measure light from a parked chair, from a moving train, from a rocket blazing across the sky, and every single time you get the same answer for how fast it travels. The speed of the beam does not care who is watching or how fast they move. Scientists first bumped into this over a century ago and were baffled. They had expected light to behave like everything else, to speed up or slow down depending on how the person measuring it was moving. Careful experiment after careful experiment said otherwise. Light kept its speed locked, stubborn, and absolute. A young man named Albert Einstein wondered about this harder than anyone. As a teenager, he liked to daydream about riding alongside a beam of light, imagining what he would see if he could pull up next to it and cruise at its pace. The more he chased that daydream, the more it fell apart. If light always flees at the same speed, then the idea of coasting beside it simply cannot happen. There is no keeping pace with something that always outruns you by the same margin. So, Einstein asked a braver question. If the speed of light truly never changes for anyone, then something else in the picture has to bend to make that possible. Speed is built out of two ingredients: distance and time. If the speed stays frozen while the person measuring it moves faster and faster, then one of those two ingredients has to stretch or shrink to keep the math balanced. That was the crack that split the old picture of reality wide open. For centuries, people assumed time was a steady drumbeat, ticking the same everywhere, for everyone, forever. A second here was a second there. Nothing could touch it. To keep light's speed truly unbreakable, Einstein realized that comforting assumption had to fall. The thing that bends to protect the speed of light is the one thing you have always trusted to hold perfectly still: your own flow of time. Speed is just distance divided by time. So if the speed of light can never change for anyone, then distance and time themselves have to give. Follow that logic where it leads and you arrive somewhere shocking. If two people measure the same beam of light and both must get the same speed, even while one of them races along at tremendous pace, then the two of them cannot be sharing the same seconds. Their clocks have to run at different rates. The faster one moves, the slower that person's time must flow. just enough to keep the speed of light coming out identical for both. This is the heart of Einstein's great leap. Time is stretchy, it is flexible, it bends. A clock that moves fast ticks slower than a clock sitting still, and this is a real physical fact about the world, woven into how the universe is built. At the speeds you live with, the effect is laughably tiny. Walk across a room, sprint down a track, ride in a car, fly in a jet, and yes, your clock slows a hair compared to someone standing on the ground. The slowdown is so small, though, that you could never feel it or spot it. Across an entire human lifetime of walking and driving, it might add up to a difference thinner than a blink. For everyday living, your time and everyone else's time march together closely enough that no one ever notices the gap. Crank up the speed, and the gap grows. Push toward a serious fraction of light speed, and the slowing of your clock becomes large, then huge, then staggering. The closer you creep to that cosmic ceiling, the more dramatically your personal time drags behind the time of the people you left standing still. When Einstein first laid this out, it sounded like a magician's tall tale. Time slowing down because you move fast, clocks disagreeing depending on their speed. For years, the idea lived mostly on paper, an elegant piece of mathematics that many people admired and few people quite believed in their gut. The obvious challenge hung in the air. Anyone could scribble equations claiming time bends. That did not make it true. A skeptic could fairly ask whether this was a real feature of the world or just a clever trick of the math, a bit of bookkeeping that happened to balance out. Picture time like a rubber band. When you barely move, the band sits relaxed, and 1 second is one plain second. Speed up, and the band begins to stretch, pulling your seconds longer and thinner compared to the seconds of someone at rest. Race near the speed of light, and the band stretches toward its breaking limit, each of your seconds ballooning into what feels like ages to the outside world. A lovely image, sure, but images prove nothing. Nature had to weigh in. Somewhere, somehow, the universe needed to show us a moving clock, actually running slow, out in the open, where anyone could check. The proof, when it came, did not arrive from a giant machine or a genius scribbling at a chalkboard. It fell out of the sky, silent and constant, in the form of ghostly little particles that have no business surviving their own plunge to the ground. Miles above your head, particles hurled from deep space are smashing into the top of the atmosphere and shattering the air into a spray of tiny fragments. These incoming bullets are called cosmic rays, and when they strike the upper air, they blast loose swarms of new particles. Among the debris is a heavy, short-lived cousin of the electron, a particle known as the muon. Muons are born high up, many miles over your head, and they come racing straight down toward the ground at breathtaking speed. Here is the catch. A muon does not live long. It exists for the barest flicker of time before it falls apart into smaller pieces. Its lifespan is so short that, even flying downward at nearly the speed of light, it should decay and vanish long before it ever reaches the surface. Do the simple math with its tiny lifetime, and the muon ought to die thousands of feet up, far above any mountaintop, let alone sea level. Yet detectors sitting right down at ground level catch muons constantly. Not a rare trickle, a steady, generous rain of them, arriving in enormous numbers, passing through the roof, through the walls, through the room you are in, through your own body, several of them every second of your life. By the old picture of time, this is impossible. The muons simply should not last long enough to make the trip. They should be ghosts that never arrive. The answer is time dilation, caught in the act. The muons are moving so close to the speed of light that their internal clocks crawl. From the muon's own point of view, only a flicker passes, exactly the short life it is allotted. From our point of view on the ground, that flicker gets stretched out, ballooned into enough extra time for the muon to finish its long plunge and reach us before it dies. Picture a candle so small it should burn out halfway through a fall from a rooftop. By every ordinary rule, it hits the pavement dark and dead. Instead, it lands still burning, flame steady, because its own sense of time slowed while it dropped. The candle experienced only a moment. The rest of us watched that moment stretch long enough to carry the flame all the way down. That is what these particles do, endlessly, right now, over your head and through your body. Every muon reaching the ground is a tiny courier delivering the same message. Move fast enough, and your time slows for real. This is measured, checked, and confirmed countless times. It is as solid a fact as gravity pulling a dropped rock to the floor. The beauty of the muons is that no one has to trust a chalkboard. The universe stages the experiment on its own, over and over, and we simply hold up our detectors and count. The count only makes sense if time truly bends with speed. There is no other way for those particles to survive the fall. So, the stretchy rubber band of time is not a daydream. It is stitched into how reality works, proven by particles falling out of the sky faster than your eye could ever follow. This same clock stretching also hides inside a small, familiar device that you probably carry in your pocket every single day. Every time your phone drops a little blue dot on a map to show where you are standing, it is quietly running the mathematics of bending time. Your phone finds your location by listening to a fleet of satellites circling high above the planet. Each of those satellites carries an incredibly precise clock, the kind that keeps time to a level far beyond any watch on your wrist. Your phone catches signals from several satellites at once, compares the tiny timing differences between them, and uses those differences to pin down exactly where you are on the surface below. For that trick to work, the clocks up in orbit and the clocks down on the ground have to agree with astonishing accuracy. Even a slip of a few millionths of a second throws the whole calculation off. And here is the trouble. Those orbiting clocks do not naturally agree with clocks on the ground because time up there runs differently. Two separate effects tug on the satellite clocks. First, the satellites are moving fast as they whip around the Earth, and that speed slows their clocks down, the same time stretching that keeps the falling muons alive. Second, the satellites float high above us, out where the pull of gravity is gentler, and weaker gravity lets their clocks tick slightly faster. One effect drags their time backward, the other nudges it forward, and the two do not cancel out. A gap is left over. Left uncorrected, that gap does not stay small for long. The tiny disagreement piles up hour after hour, and within a single day, it would throw your position off by several miles. Your map would confidently plant your blue dot in the wrong town. Your directions to a friend's house would send you drifting farther and farther from the right street with every passing hour. The only reason your phone works is that the engineers who built the satellite system planned for all of this from the start. They deliberately tuned the orbiting clocks to account for the bending of time, adjusting them so that, once the effects of speed and gravity are folded in, the satellite clocks and the ground clocks end up matching. Relativity is not some far-off theory scribbled in a dusty book. It is switched on and running inside the navigation that guides millions of people through traffic every single day. Think of it like two clocks that stubbornly refuse to keep the same time, one resting in your pocket and one soaring in orbit far above your head. Left alone, they slowly drift apart. To keep them in step, someone has to know the exact rules for how time bends with speed and height, then correct for it down to the millionth of a second. That is the wild part. This is not a rare laboratory curiosity. It is baked into an everyday tool that billions of people treat as ordinary. The bending of time is so real, so reliable, and so precisely understood that we build machines that depend on it and trust our daily travels to it. A satellite, though, feels only a gentle version of this. It moves fast for a machine, but it is still creeping compared to a beam of light, so its clock only drifts by the tiniest sliver. Now imagine taking a living human being, strapping them into something far faster, and flinging them toward the speed of light. The gentle drift a satellite feels would swell into something enormous, strange, and almost impossible to believe. Imagine two twins who have never spent a single day apart. Right up until the morning, one of them climbs into a rocket and the other stays behind. The traveling twin straps in, the engines roar, and the ship tears away from Earth, building up to a speed close to the ultimate limit of the universe. It races out toward a distant star, swings around, and comes flying back home. For the twin on board, the whole round trip feels reasonably short. A handful of years pass inside the ship. They eat, they sleep, they watch the stars slide by, and before too long they are back where they started. Then the hatch opens, and the traveler steps out into a shock. The twin, who stayed on Earth, has grown old. Decades have rolled past on the home planet. The stay-behind twin has lived a whole life in the meantime, with grey hair, wrinkles, and a lifetime of birthdays stacked up. The traveler, meanwhile, has barely aged at all, still young, still fresh-faced, staring at a sibling who now looks old enough to be a parent or grandparent. Both twins lived through the same journey, and both are completely right about what they experienced. The difference is that the traveler's clock genuinely ran slow the entire time the ship was racing near light speed. Fewer seconds ticked by for the one in motion. The rocket did not just seem to slow time, it actually did, for the person inside, measured against everyone left on the ground. This sounds like pure fantasy, the kind of thing that only works in a story. It has been checked in the real world, though, in a smaller and gentler form. Scientists took super-precise atomic clocks, the same reliable kind used to keep official time, loaded them onto jet planes, and flew them around the world. When those flying clocks came back and were compared against identical clocks that had stayed on the ground, they disagreed, by a tiny fraction of a second, in exactly the direction and amount that the bending of time predicted. The moving clocks had aged a hair less than the still ones. Picture two runners on the same track, starting together and finishing together. One took the ordinary path. The other somehow moved through a stretch of track where time itself flowed slower. They crossed the finish line at the same moment by the stadium clock, yet one of them has aged noticeably less than the other during the very same race. That is the twin on the rocket. Same start, same finish, different amount of life used up along the way. The size of the effect depends on speed. Fly a jet, and the difference is almost nothing, a whisper of a fraction of a second. Fly a rocket near the speed of light, and the difference explodes into decades. The closer you push toward that cosmic ceiling, the more brutally your clock slows compared to the world you left behind, and the wider the gap in age grows when you finally come home. So, the pattern is clear and proven. Speed steals time. The faster you move, the fewer seconds you spend, and the younger you stay compared to everyone standing still. Which leads straight to a dizzying question. If moving near light speed slows a traveler's clock this dramatically, what happens to that clock when you stop merely approaching the speed of light and imagine reaching it exactly? The answer pushes past strange and into something that feels almost impossible. Take that rocket and refuse to stop pushing. Past fast, past incredibly fast, right up to the razor-thin edge of light speed itself. At each new level of speed, the traveler's clock slows more sharply than before. Fly at half the speed of light, and time drags a little. Fly at 9/10, and the slowdown becomes serious. The traveler aging noticeably slower than the world outside. Push to 99%, and the effect turns severe. Now, for every year that passes on the ship, about 7 years pile up back on Earth. The traveler grows 1 year older, while their home planet burns through 7. Keep climbing. At 99.9% of light speed, the gap yawns wider still. 1 year on the ship stretches into more than 20 years outside. The traveler ages a single year while over 2 decades roar past in the rest of the universe. Nudge the throttle closer, and the numbers grow monstrous. A single day inside the ship could swallow centuries beyond the windows. This is the wild truth hiding inside speed. The closer you creep toward that final limit, the slower your own seconds crawl, and the more staggering the amount of outside time you skip. A traveler flying close enough to light speed could set out on a short personal voyage, feel only a few years pass, and return to find that thousands of years had swept over the earth. Whole civilizations could rise and fall while the traveler barely ages past their youth. And the growth does not slow down as you approach the limit. It speeds up. The slowdown of your clock grows gentle at low speeds, then punishing near the top, rising faster and faster the closer you press to the edge. Each tiny step nearer to light speed costs an enormous jump in how much outside time flies by. Picture climbing a hill that gets steeper with every step. Near the bottom, the slope is easy, and the path barely tilts. As you rise, the ground pitches up harder and harder, until near the summit the wall is so steep it seems to rise almost straight up in front of your face. Reaching the very top would mean climbing a cliff that stands perfectly vertical, an impossible final step. That final step is the speed of light. For anything with weight, that summit can never be touched. A rocket, a particle, a human body, all of it can climb terrifyingly high up the slope, hugging the edge, feeling time crawl to a near standstill, yet the very top stays forever out of reach. The closer a heavy object creeps to light speed, the more energy it takes to squeeze out even a sliver more speed, and the cost climbs without end. You could pour in all the power in every star in the galaxy and still fall short of the line. So time never quite freezes for anything that carries mass. It only crawls slower and slower, approaching a stop it can never actually reach. A traveler can get breathtakingly close, aging a heartbeat while eons pass outside, and still their clock keeps ticking, faint but alive. That leaves one haunting possibility unexplored. Everything so far has been about heavy things creeping toward the limit. What about something that already sits at the very top, riding the speed of light with no effort at all? To understand what happens to time there, we need the exact rule that governs the entire climb. Behind every one of these dizzying numbers sits a single rule, one clean piece of mathematics that decides exactly how much time bends at any speed. Scientists call the heart of this rule a stretching number. You can think of it as a multiplier that tells you how badly time slows for a moving object. When something sits still or crawls along slowly, the stretching number sits at 1. Multiply time by 1 and nothing changes, so a slow object ages at the normal, familiar rate. This is why walking across a room does nothing you could ever notice. Your stretching number is basically 1. As speed climbs, the number climbs with it. At half the speed of light, it rises a little above 1, so time slows a little. At 99%, the number jumps to about 7, which is why 1 year on the ship becomes 7 years outside. At 99.9%, it leaps past 20. The number is simply the amount by which outside time gets multiplied compared to the traveler's time. What makes this rule so strange is the way the number behaves near the top. For most of the journey up the speed scale, it grows politely, inching upward as you speed up. Then, as you close in on the speed of light, it stops behaving politely and starts to explode. Tiny nudges in speed near the edge send the number rocketing upward, faster and faster, with no ceiling in sight. Here is the piece that matters most. As speed presses right up against the speed of light, this stretching number does not settle on some big final value. It races toward infinity. It grows without limit, larger than any number you could ever write down, no matter how many zeros you add. An infinite stretching number would mean an infinite slowdown of time. And an infinite slowdown means time does not merely crawl, it stops. Picture a spring being pulled longer and longer. At first, it stretches easily, gaining a little length for each tug. As you keep pulling, it fights back harder, and near its limit, even a gentle tug stretches it wildly. The stretching of time works the same way, except this spring has no final length at all. Pull it toward the speed of light, and it stretches without end, longer and longer, toward forever. This is exactly why anything with weight can never reach the speed of light. To slow a massive traveler's time by an infinite amount, you would need to pour in an infinite amount of energy. And infinite energy is something the universe simply cannot supply. The rule slams the door. Heavy things are locked below the limit, always climbing, never arriving. Yet the rule does something curious when you stop asking about heavy travelers and start asking about the speed of light itself. Instead of describing a journey that keeps climbing forever, it points to a single, frozen answer. A place where the stretching of time has already gone all the way to its impossible end. For a beam of light, the stretching number is not merely large, it has run off the edge of the scale completely. And when you follow that all the way to its conclusion, you arrive at the strangest clock in the entire universe. One that has stopped so completely it never ticks even once. Feed the speed of light directly into the rule for how time bends, and the mathematics stops handing back ordinary numbers. For every speed below the limit, the rule gives a clean answer. Half of light speed gives one number. 99% gives another. Each answer is a real figure you can hold, a specific amount by which time slows. Slide all the way up to the speed of light itself, though, and the rule breaks past every finite answer. The slowdown does not land on some enormous value, like 1,000,000 or 1,000,000,000. It shoots straight to infinity, the endless, off-the-scale result that no normal number can capture. An infinite slowdown carries a blunt meaning. If time slows by an infinite amount, then time is not passing at all. The clock does not crawl. It does not creep by one sliver of a second per century. It halts completely and forever, frozen at a dead stop. So, a beam of light travels with a clock that never moves. Not slowly, not almost frozen. Stopped. From the moment light is born to the moment it is caught, its own clock reads exactly the same, ticking off precisely 0 time along the entire trip. 0, no matter how short the hop or how vast the voyage. Let that settle against everything from the last few chapters. A rocket near light speed slows its clock to a crawl, aging 1 year while decades or centuries fly past outside. Push it faster, and the crawl grows even slower, closer and closer to a stop, yet always still a crawl, always still ticking faintly. Light has already arrived at the destination every rocket strains toward and can never reach. Its clock has stopped entirely. That is the deep divide between light and everything else. Heavy things climb the slope forever, approaching the frozen summit without touching it. Light is not climbing. Light lives at the summit. It sits at the one place in the universe where time has run all the way down to nothing. Picture a stopwatch dropped into a block of solid ice, the hands locked in place, unable to twitch even a hair. Now imagine that ice is so perfect and so total that the hands will never move again, not in a second, not in 1,000,000,000 years. That frozen stopwatch is the clock every beam of light carries. It was stopped the instant the light was born, and it stays stopped for the whole journey, however long that journey looks to the rest of us. There is a strange kind of order in this. Slow objects have clocks that run nearly normal. Fast objects have clocks that run slow. Objects near light speed have clocks that barely move. And light, at the very top, has a clock that does not move at all. The pattern points cleanly to a single, frozen endpoint, and light is sitting right on it. This is the quiet answer behind the whole mystery we started with. Old starlight arrives fresh and pristine after billions of years because, for the light itself, no time has passed to wear it down. It never got the chance to age. Its clock was stopped the whole way across. If a beam of light truly spends 0 time on its trip, then something bizarre happens to the two most important moments in that beam's whole existence: the moment it is created and the moment it dies. For a beam of light, the moment it is born and the moment it is caught are pressed together into one single instant. Follow the logic from the frozen clock, and this is where it lands. If a photon's own clock ticks off exactly 0 time from the moment it leaves a star to the moment it strikes your eye, then from the light's own reckoning, no gap separates those two events at all. Birth and arrival happen together. The flash of creation and the flash of being absorbed are the same moment, with nothing in between. Sit with how strange that is. To you, watching from the outside, a beam of light clearly takes time to travel. It leaves the sun, and 8 minutes later it warms your face. Those are two separate moments, 8 minutes apart, plain as day. But that 8 minutes belongs to your clock, the clock of an outside observer standing still. For the light itself, carrying its stopped clock, there is no 8 minutes. There is only a single instant that holds both leaving and arriving at once. Stretch the distance, and the point sharpens. A beam that crosses the galaxy for 100,000 years, by our clocks, still experiences the very same thing as the 8-minute sunbeam. From the light side, 0 time passes. Creation and capture remain fused into one moment. The staggering length of the trip, all those thousands of years we measure, simply does not exist for the light. It is born and it lands in the same breath, whether the road was short or unthinkably long. Every beam of light in the universe carries this secret. The glow from your bedside lamp crossing a few feet of air, and the glow from a galaxy at the far rim of the visible cosmos, crossing billions of years, both live the exact same instant. For each of them, leaving and arriving are one event. The only thing that changes is how long the trip looks to those of us standing still and watching. Picture a bridge stretched across a canyon. To anyone watching from the canyon rim, the bridge is long, and crossing it clearly takes time. Now imagine a traveler for whom the two ends of the bridge are the same spot, the near edge and the far edge touching, so that stepping on and stepping off are a single motion with no walk in between. That is what every distance looks like to a beam of light. Both ends of every journey are fused together, and the crossing takes no time at all. This is why light is such a perfect messenger across the cosmos. It does not experience the wait. It does not sit through the long, dark crossing, growing old and worn. From its side, there is no crossing to sit through. It simply is at the star, and then it simply is at your eye, with those two states melted into one flash of existence. To be careful and honest, this describes what the mathematics says about the light's own frame, a frame that comes with a serious complication we will face head-on soon. For now, hold the picture. Every beam is born and caught in the same instant. Its whole voyage collapsed to nothing. That idea sounds abstract until you point it at a single old star and realize what it truly means for the ancient light landing in your eye tonight. Somewhere out in the dark tonight sits a star whose light has been racing toward Earth since long before any human, any mammoth, or any dinosaur ever walked the planet. Say that star sits 65 million light-years away. The light leaving its surface tonight, by our clocks, set out 65 million years ago, back when the last of the great dinosaurs still roamed. That beam launched into the dark, crossed an ocean of empty space wider than the mind can picture, and only now, after 65 million years of our time, slips quietly into a telescope on Earth. By every ordinary measure, that light should be ancient. 65 million years is longer than our whole species has existed, longer than the age of most mountain ranges, a stretch of time so vast it makes recorded history look like a single heartbeat. Anything that traveled that long should be worn to dust. The light arrives perfect. It carries the exact color the star had when the beam was born, the precise fingerprint of the star's chemistry and heat, sharp and unspoiled. Astronomers can spread that ancient light apart and read the star's ingredients as easily as reading a fresh label, because nothing about the beam has faded or decayed on the way. Here is why. For that beam of light, those 65 million years never happened. Its clock read 0 the entire trip. From the light's own side, it left the dinosaur-era star and struck the telescope in the same single instant, with no long crossing in between. The star's light did not spend 65 million years growing old, because for the light, no time passed at all. It arrives fresh because, from its point of view, it was made only a moment ago. This is the resolution of the puzzle that opened this whole journey. Old starlight looks crisp and new because, in a real sense, it is new. The vast age we assign to it belongs to our clocks, to us watching from the outside. The light itself never aged a second. Every ancient beam is, from its own side, freshly born, the instant it lands. Picture a letter sealed inside a bottle and thrown into the sea, drifting for 65 million years before washing up on a beach. By all rights, the paper should be rotted, the ink long gone, the message lost. Instead, the bottle opens and the letter inside is crisp and white, the ink still wet as if written moments before. That is starlight. The journey took an eternity by our reckoning, yet the message arrives as fresh as the moment it was written, because for the letter, no time went by. This gift is the reason we can study the deep past of the universe at all. Every distant object we point a telescope at hands us a perfect, unfaded snapshot of how it looked when its light departed. The farther we look, the deeper into the past we see, and the light delivers each ancient scene in flawless condition, untouched by the ages it crossed. So light does not merely resist aging, it skips aging completely, arriving new no matter how long the road. And if time collapses to nothing for a beam of light, then something equally shocking has to happen to the other half of the picture, the distance itself. If a beam of light spends zero time crossing the universe, then a fair question follows. What happens to the enormous distance it supposedly crosses? The bending that Einstein uncovered does not touch time alone, it grips space as well. Just as a fast traveler's clock slows down, a fast traveler's ruler shrinks. Distances in the direction of motion squeeze shorter the faster you go. At everyday speeds, the shrinking is far too tiny to notice. The same as with time. Push toward the speed of light, though, and the squeezing grows fierce, distances collapsing shorter and shorter along the path of travel. Follow that all the way to the top and the result is jaw-dropping. For a beam of light, distances in the direction it travels do not merely shrink, they collapse to nothing. From the light's own side, the space it crosses is squeezed flat to zero length. The star it left and the eye it lands in are pressed together with no gap between them at all. This locks together perfectly with the frozen clock. Time collapses to zero, and distance collapses to zero, hand in hand. For the light, there is no long journey through time and no long journey through space, because both have been squeezed down to nothing. The star and the destination sit in the same instant and the same place, fused into one point. That is why creation and arrival happen together. There is no distance to cross and no time to spend. So the universe that looks unimaginably vast to us looks like nothing at all to a beam of light. The billions of light years we measure between galaxies, all that yawning emptiness, is flattened to zero from the light's point of view. To us, the light spends billions of years crossing an ocean of space. To the light, the far shore is already touching the near shore, and there is nothing to cross. Picture a long strip of paper with a star drawn on one end and an eye drawn on the other. To you, the strip is long, and getting from the star to the eye means traveling its whole length. Now fold the paper so the two ends touch, the star pressed flat against the eye with the entire strip crushed to nothing in between. That fold is what light experiences. Both ends of every voyage are pressed together, and the vast strip of space simply vanishes. This is the full shape of the mystery. A beam of light lives in a universe with no time and no distance. Every journey, however long it looks to us, is for the light a single motionless instant in a single flattened point. It does not travel across the cosmos so much as it simply touches both ends of the trip at once. There is something almost dizzying about holding both views in your head at the same time. From where we stand, light races across a huge, ancient universe for billions of years. From where the light rides, there is no race, no size, no age, just an instant with the two ends of everything pressed together. All of this rests on one bold move, imagining what the world looks like from the light's own point of view. And that move hides a serious catch, one that careful scientists insist we face squarely before going any further. Everything just described came from stepping into the light's own point of view. And here is the honest truth. Physics says that point of view cannot actually exist. The rules that let us bend time and squeeze distance work by comparing one moving observer to another. You pick a speed below the limit, plug it into the rule, and out come real answers about slowed clocks and shrunken rulers. The whole machinery is built for observers traveling slower than light. It runs smoothly at half light speed, at 99%, at 99.9%, giving clean numbers every time. Try to plug in the speed of light itself, though, and the machinery jams. The rule stops producing usable answers and instead spits out infinities and zeros, the mathematical signs that you have pushed the tool past where it is allowed to go. Dividing by zero, chasing endless quantities, the equations throw up their hands. They are telling you that a genuine point of view riding along with the light is off limits. There is no valid frame of reference for a beam of light. The theory forbids one outright. So, when we talk about the light experiencing zero time, or seeing distances flatten to nothing, we are stretching the language past its safe zone. We are taking the pattern the rule shows for slower and slower travelers, and imagining where it points at the very end. The clock slows toward a stop, the ruler shrinks toward nothing. The pattern clearly aims at zero time and zero distance. Yet the light itself never truly occupies a seat from which to look out and see any of it. This matters, and careful scientists are firm about it. A beam of light is not a tiny traveler peering out a window, watching the universe flatten around it. It has no window and no viewpoint. The idea of the light's own experience is a useful mental picture, a way to feel where the mathematics leads, and nothing more. The light does not perceive, does not observe, does not sit and marvel at a collapsed cosmos. Zero proper time is a statement about the shape of space-time along the light's path, not a claim that the light is aware of anything. Picture standing between two mirrors that face each other, watching your reflection repeat smaller and smaller into the distance, on and on toward a vanishing point. You can clearly see where the shrinking reflections are heading, toward a final image at the very end of the tunnel. Yet that final image is never actually there. It is the place all the reflections point toward, a limit they approach but never reach. The light's point of view is like that vanishing point, real enough to aim at, impossible to actually stand in. So hold both things at once. The mathematics genuinely shows that time and distance run all the way down to zero along the path of a beam of light. And at the same time, the light has no true perspective from which to experience that zero. The pattern is real. The passenger is not. None of this weakens the core fact. Light carries a stopped clock and crosses a flattened space, and that is why old starlight arrives fresh. It simply means we should speak carefully, describing what the geometry says rather than pretending the light is a little tourist. That raises a sharper question. If light is forced to sit at this impossible edge of zero time, what is it about light that locks it there, unable to ever slow down and join the rest of us? Every object you have ever touched can speed up or slow down at will, yet a beam of light is trapped at one single speed and can never budge from it. Throw a baseball, and it leaves your hand fast, then slows as it flies, then stops when it lands. Roll a marble, and it drifts to a halt. Everything made of solid stuff can move at any speed you like, from a dead stop all the way up toward the cosmic limit, and it can change that speed freely. Light cannot. In empty space, light always travels at exactly one speed, the full speed limit of the universe, and it can never go slower and never go faster. It has no other setting. The reason comes down to a single property: weight, or more precisely, mass, the amount of stuff a thing is made of. A baseball has mass. A marble has mass. Your body has mass. Anything with mass is forbidden from ever reaching the speed of light, because shoving a massive object up to that limit would take an endless supply of energy, as we saw with the impossible vertical cliff at the summit. Light is different in the most fundamental way possible. The particles that make up light, called photons, have no mass at all. They are made of pure energy with zero weight. And here is the rule that changes everything. Anything with zero mass, is not merely allowed to travel at the speed of light, it is forced to. A massless thing has no choice. It must move at exactly that speed, always, the instant it exists. So, a photon is born already moving at the full speed of light. It does not start slow and speed up. It does not accelerate from a standstill. The moment it comes into being, it is already flying at the ultimate limit, and it stays there for its entire life. It cannot slow down to catch a breath, cannot pause, cannot idle. Zero mass means one speed, locked in forever. This is the flip side of the cliff we climbed earlier. Massive things can never reach the top because they have weight dragging them back, demanding endless energy to climb. Massless things are stuck at the top for the very same reason turned inside out. With no weight to hold them below the limit, they have nowhere to sit except the summit itself. The very property that traps heavy objects below the speed of light is the property that pins light exactly on it. Picture a line of swimmers in a river. The heavy swimmers, loaded with weights, can paddle at any pace they choose, but can never quite reach the fierce current racing down the center. The weightless swimmers have no such struggle and no such choice. The instant they enter the water, the current seizes them and sweeps them along at its full speed, unable to slow, unable to drift, carried at one unchanging pace forever. Light is the weightless swimmer borne straight into the fastest current there is. And because light is forever pinned at that one speed, it is forever pinned to the frozen clock and the flattened space that come with it. Its lack of weight is exactly why it never ages. Mass would let it slow down and feel time. Without mass, it can only ride the edge where time has stopped. This raises a tempting escape hatch. If light never ages on its own, could something out in the vast dark still reach in and wear it down over billions of years? If a beam of light never ages by its own clock, a clever objection appears. Surely, over billions of years of travel, something out there must slowly wear it down. It sounds reasonable. Everything else in the universe decays given enough time. Iron rusts, mountains erode, stars burn out. Across billions of years, even the toughest things crumble. So why should light be immune? Maybe, the thinking goes, light does grow tired on its long crossing, losing a little energy with each passing eon, fading gradually until it limps into our telescopes as a worn-out shadow of what it once was. Scientists took this idea seriously long ago. They noticed that light from distant galaxies arrives shifted toward the red end of the color scale, stretched to longer, redder wavelengths, and the farther the galaxy, the greater the shift. One tempting explanation was that light simply gets tired over enormous distances, leaking energy into empty space along the way, which would redden it and dim it as it traveled. This became known as the tired light idea. It was a fair guess, and the beauty of science is that a fair guess gets tested rather than trusted. Astronomers went looking for the fingerprints such tiredness would leave behind. If light truly bled energy across billions of years of travel, that draining would blur distant objects, smearing their sharp features into a haze, and it would redden light in a particular pattern that could be checked against the sky. The evidence said no. Distant galaxies arrive sharp, not smeared. Their light shows crisp, clean detail that tired, energy-leaking light could never preserve across such distances, and the exact way the light is shifted fails to match what a slow draining of energy would produce. Careful measurement after careful measurement ruled the tired light idea out. Light does not grow weary on its journey. It does not leak away its energy into the dark. This fits everything we have built. A beam of light carries a stopped clock. With no time passing for the light, there is no stretch of eons during which it could slowly wear down. Aging requires time, and light has none. It cannot grow tired for the same reason it cannot grow old. From its own side, the long crossing never happened, so there is no journey during which anything could drain it. A photon left utterly alone in empty space is, as far as we can tell, close to immortal. It does not decay, it does not fall apart, it does not fade with age. It can fly for the entire history of the universe and remain exactly the photon it was born as, carrying the same energy it started with, ready to deliver its message intact whenever it finally lands. Picture a candle flame that never burns down. Ordinary flames eat their wax and shrink toward darkness. But this flame draws on nothing and loses nothing, holding its exact shape and brightness, whether it burns for a second or forever. That is a photon crossing empty space. Untouched by time, it neither shrinks nor dims, immortal until the moment something absorbs it. So the escape hatch is closed. Nothing in the empty dark reaches in to age a beam of light. It arrives fresh because it truly is untouched. Yet, light does change on its long voyage in one specific way, a change that has nothing to do with growing tired and everything to do with the universe itself stretching beneath the light's feet. While a beam of light flies across the cosmos, the space it is flying through does not sit still. It is stretching. The whole universe is growing. Every patch of space is slowly swelling outward, carrying the galaxies farther apart with each passing age. This is one of the biggest discoveries ever made about the cosmos. Confirmed beyond any doubt, space itself expands, like the surface of a balloon inflating, with the galaxies riding along as painted dots that drift apart as the balloon grows. Now think about a beam of light crossing that swelling space. The light holds its frozen clock and never ages. That part stays true, but the space it travels through keeps stretching underneath it for billions of years. And as the space stretches, it pulls on the light riding through it, tugging the light's waves longer and longer. Light travels as tiny waves, and the length of those waves decides its color. Short waves look blue, longer waves look red. Stretch the waves out, and the color slides toward the red end of the scale. So a beam that leaves a distant galaxy looking bluish can arrive at our telescopes looking distinctly red, its waves pulled long by all the space that swelled beneath it during the trip. Scientists call this cosmological redshift. The farther the light has traveled, the more stretching space it has crossed, and the redder it arrives. Light from a nearby galaxy is barely shifted. Light from a galaxy near the edge of what we can see arrives shifted enormously, its waves stretched many times longer than when they began. Notice what changed and what did not. The light did not grow tired. It did not leak energy into the dark or fade from age. The universe simply stretched, and that stretching pulled the light's waves along with it. The change comes from the space, not from any weariness in the light. From the light's own frozen side, still nothing happened at all. The stretching is something we see from the outside, a fingerprint left on the light by the growing cosmos it crossed. Picture drawing a short, wavy line on a rubber sheet, then grabbing the edges and pulling the sheet wide. The line does not fade or break. It simply stretches, its little waves spreading out longer and flatter as the sheet grows beneath it. That rubber sheet is space, and the wavy line is a beam of light. Pull the sheet across billions of years, and the light's waves stretch long, sliding its color toward red. This gives astronomers something priceless. By measuring exactly how much a galaxy's light has been reddened, they can work out how much space has stretched since that light departed, which tells them how far away the galaxy sits and how long ago the light began its trip. The redder the light, the more the universe has grown since it set out, and the deeper into the past we are peering. So the stretch of the light becomes a kind of yardstick and a kind of clock rolled into one. Read the redness, and you read both the distance and the age. The most reddened light we catch has crossed almost the entire history of the cosmos, stretched by the expansion of nearly the whole universe. That yardstick lets us do something staggering. It lets us find the single oldest light in all of existence, a glow that has been stretching since almost the very beginning of everything. Follow the reddest, most stretched light all the way to its limit, and you arrive at a glow older than any star, a glow left over from the birth of the universe itself. Long before there were galaxies or stars, the entire cosmos was a searing hot fog, packed dense and glowing like the inside of a furnace. Everything, everywhere, blazed with light and heat, so crowded and bright that light could not travel freely. It bounced around, trapped inside the glowing fog, unable to strike out across open space. Then, as the universe grew and cooled, the fog cleared. All at once, across the entire cosmos, the trapped light was set free to fly. That released glow has been streaming through space ever since, for nearly the whole age of the universe. Longer than any starlight, longer than anything else we can detect. It is the oldest light there is, the leftover shine of the newborn cosmos. And here is the astonishing part. That ancient glow is still arriving right now, from every direction at once. It fills all of space. Point a sensitive detector at any empty patch of sky. Up, down, sideways, and the same faint glow comes streaming in, the afterlight of the beginning washing over the whole earth continuously. We are soaking in the oldest light in existence every second of every day. This glow carries the frozen clock like all light does, so from its own side, no time has passed since the fog cleared. Yet the space it crossed has stretched by an enormous amount over all those ages, one of the biggest stretches any light has ever endured. That stretching pulled its waves out to a staggering length, shifting it far past red, past the colors your eye can see, all the way into a kind of light your eyes cannot catch at all. When this glow was born, it was blindingly bright and furnace hot, thousands of degrees, fierce enough to light the whole sky in every direction. Today, stretched by the growth of the cosmos across billions of years, it has cooled to a whisper, one of the coldest, faintest things we can measure, barely a breath above the absolute lowest temperature possible. The same light that once blazed like a furnace now drifts in as a cold, gentle hum from the dawn of everything. Picture a photograph of a room taken at the exact instant a giant flashbulb went off, capturing the whole scene in one blinding burst. Now imagine that single burst of light from that one first instant, still faintly traveling and still faintly arriving billions of years later, stretched and cooled, but carrying the same ancient snapshot. That is the glow filling the sky, a baby picture of the entire universe, delivered fresh to us right now, because for the light no time passed at all. Scientists treasure this glow above almost anything else in the sky, because it is a direct message from the newborn cosmos, unaged and intact. Reading it, they can map what the universe looked like in its very first chapter, when there were no stars, no planets, only glowing fog beginning to clear. That oldest glow marks the earliest thing we can ever see. Try to look past it, back toward the very first instant, and we run headfirst into a wall that light itself cannot cross. Push your telescope back through time as far as it can reach, and you slam into a wall of glowing fog that no light can pierce. That ancient glow filling the sky comes from the moment the fog cleared, the moment light was first set free to travel. Before that moment, the universe was too hot, too dense, too crowded for light to move at all. Every beam that tried to cross was instantly scattered, bounced, and swallowed by the thick, glowing haze. Light was trapped, unable to carry any clean message across space. So when we look outward and backward, we can see all the way to the instant the fog lifted, and no further. That glowing wall is the deepest thing any telescope will ever show us. Behind it lies the first stretch of the universe's life, and it is hidden from every eye, because during that time no light could escape to carry the scene to us. Think about how strange that limit is. We can see light from the moment the cosmos became clear, a time when the universe was only a few 100,000 years old. That sounds ancient, and it is. Yet, the universe had already been growing for those few 100,000 years before the fog lifted, and that opening chapter stays sealed behind the wall of glowing haze. Light simply cannot bring us any picture from before the fog cleared. This is a hard limit, baked into the nature of light and matter, and no better telescope will ever get around it. You could build an instrument 1,000 times sharper than anything we have, and it would still stop at the same glowing wall. The barrier does not come from weak equipment. It comes from the fact that light itself could not travel through the early fog, so there is no light from that era to catch. There is something humbling in it. Light is our one and only messenger from the deep cosmos. Everything we know about the distant universe, we know because light carried it to us across space and time. And light draws a firm line. It can show us everything from the moment the fog cleared onward, delivering each scene fresh and unaged. It can show us nothing from before, because before that, it had no freedom to fly. Picture standing at the edge of a thick bank of fog rolling off the ocean. You can see clearly right up to the wall of mist. Every wave and rock in front of it sharp and bright. Past that wall, the fog swallows everything. You know there is more ocean out there, more waves rolling in the distance, yet no light reaches you from beyond the mist. The glowing wall at the dawn of the universe is exactly that fog bank, marking the farthest edge of everything light can ever reveal. To peer behind that wall, scientists have to hunt for messengers other than light, faint signals that could have slipped through the early fog when light could not. Those hunts are difficult and still unfolding, at the very frontier of what we can detect. For now, light hands us a perfect view of everything from the clearing of the fog onward, and among the treasures it delivers are the faint, reddened glimmers of the very first galaxies, born in the darkness just after the wall. Just past the glowing wall, in the first darkness after the fog cleared, the earliest galaxies flickered to life, and their ancient light is only now reaching us. Astronomers have built a telescope so powerful it can catch these faint first galaxies, their light stretched far into the red by all the space that swelled during the trip. Recently, that telescope caught a galaxy so distant that its light left when the universe was staggeringly young, only a few 100 million years past the very beginning. By the reckoning of our clocks, that light has been racing toward us for close to the entire age of the cosmos before landing in the telescope's mirror. This galaxy sits near the edge of everything we can see, deep in the era scientists call the cosmic dawn, when the first stars and galaxies were just igniting in a universe that had known only darkness and glowing fog before them. The light it sent us shows that galaxy as a newborn, a bright cluster of the very first stars blazing in the young cosmos. We are seeing a scene from the childhood of the universe, delivered to us in pristine condition, and pristine is the right word, because of everything we have learned. That light spent close to the whole history of the universe crossing space by our clocks. Yet for the light itself, the frozen clock read 0 the entire way. From the light's own side, it left that newborn galaxy and struck our telescope in the same instant. It arrives fresh, carrying a perfect snapshot of the cosmic dawn, unaged by the eons it crossed. The stretch on that light is enormous, one of the largest ever measured. Its waves were pulled out many times longer than when they left the galaxy, shifted so far into the red that only a specially built telescope, tuned to catch that deeply reddened light, could see it at all. To ordinary eyes and ordinary instruments, this ancient galaxy is invisible. Its light stretched past the range we can normally detect. Catching this glimmer is like receiving a letter written by a child who has long since grown old. A letter that somehow arrives with the ink still wet. The galaxy we see in that light no longer looks the way the light shows it. Over the billions of years the light was traveling, by our clocks, that galaxy kept growing, its stars aging and dying, new ones being born. The version we see is frozen in its infancy, a perfect record of a moment that passed away almost the entire history of the universe ago. This is the deepest gift light gives us. The farther we look, the further back in time we see, and light delivers each ancient scene flawless and fresh, untouched by the ages it crossed. By hunting the faintest, reddest glimmers, astronomers can watch the universe's earliest chapters play out, catching the first galaxies as they truly looked when they first switched on. Every new record pushes a little closer to that glowing wall, a little deeper into the cosmic dawn. Each fresh discovery catches a galaxy younger and more distant than the last, sending its ancient light across nearly the whole span of time to reach a mirror on a telescope floating in space. Yet, even this deep view has an outer boundary, an edge to everything light can ever bring us, a bubble beyond which the universe hides forever. Everything we can ever see sits inside an invisible bubble, a boundary marking the farthest that any light has had time to travel to us since the universe began. The cosmos has been around for a vast but finite stretch of time. Light, fast as it is, still needs time to cross space. So, in all the ages since the beginning, light has only been able to travel a certain maximum distance before reaching us. Anything closer than that distance, its light has had time to arrive. Anything farther, its light simply has not gotten here yet. That maximum reach forms a giant bubble around us, and everything we will ever see lives inside it. Scientists call this bubble the observable universe. It is not the whole cosmos. The universe almost certainly stretches far beyond the bubble, likely much farther, perhaps endlessly. We just cannot see those outer regions, because their light has not had enough time to cross the enormous gulf and land in our telescopes. The bubble marks the edge of the visible, the limit of what light has managed to deliver. Here is a mind-bending twist. Because the light reaching the edge of the bubble left its source near the very beginning and traveled almost the entire age of the universe to get here, and because space kept stretching the whole time, the actual objects at that edge are now much farther away than the light's travel would suggest. The light took a long journey to reach us, and while it traveled, its home galaxies drifted even farther out with the growing space. The edge of what we can see sits tens of billions of miles beyond miles, a distance so huge that ordinary numbers lose all meaning. Every one of us sits at the center of our own bubble, simply because the light arriving here has traveled from all directions to reach this one spot. Someone in a distant galaxy would have their own bubble, centered on them, reaching out into regions we can never see and missing regions we can. There is no true center of the cosmos. Each observer sits at the middle of their own patch of visible universe, ringed by the light that has had time to arrive. Picture standing in the middle of a wide, dark field at night, holding a lantern, while friends stand scattered far off in the dark, each holding their own lantern. You can see the lanterns close enough that their light has reached your eyes. Friends too far away, their light is still crossing the field toward you and has not arrived. Around you sits a circle of light you can see, and past it, a darkness full of lanterns whose glow is still on its way. That circle is your observable universe. This bubble is not a wall in space. Nothing special sits at its edge. It is simply the distance light has managed to cover in the time available, a horizon set by the speed of light and the age of the cosmos. As time passes, the bubble slowly grows, and light from a little farther out gets the chance to reach us, revealing regions that were hidden before. So more of the universe should keep coming into view as the ages roll on. That would be true, except for one cruel fact about the growing cosmos, a fact that turns the story upside down and begins to steal galaxies away from us forever. The universe is not merely growing, its growth is speeding up, and that acceleration is quietly carrying distant galaxies out of our reach for good. For a long time, scientists expected the expansion of the cosmos to gradually slow down, dragged on by the pull of all the matter inside it. Careful measurements revealed the opposite. The expansion is picking up pace, pushing the galaxies apart faster and faster as time goes on. Some mysterious property of empty space itself seems to be driving this speed up, and it dominates the future of the whole universe. Here is what that acceleration does to light. Space between us and a very distant galaxy is stretching, and the farther the galaxy, the more total space lies between us, and the faster that whole gap grows. Past a certain distance, the space between us and a galaxy stretches so quickly that light leaving that galaxy can never make up the ground. The light flies toward us at its full speed, yet the space ahead of it swells faster than it can cross. The light loses the race. So there are galaxies out there whose light will never reach us, no matter how long we wait, not because the light is slow, but because the road keeps lengthening faster than the light can travel it. Those galaxies are slipping beyond a boundary of no return, a horizon past which their light is forever cut off from us. Once a galaxy crosses that line, we will never receive another beam from it again. And the boundary is closing in. As the expansion accelerates, more and more galaxies cross that line and vanish from our future view. The light they send after crossing simply piles up against the ever-growing gap and never arrives. One by one, over enormous stretches of time, the distant galaxies are being carried out of reach, their last light draining away into red and dark. This means the far future sky will be lonelier than the sky we enjoy today. Right now, we can see a universe brimming with galaxies in every direction. Ages from now, so much of the cosmos will have raced beyond the horizon of no return that only our closest galactic neighbors will remain visible. Anyone living then, looking out, would see a small, quiet sky with the rest of the universe hidden forever behind the runaway stretch of space. Picture a swimmer trying to reach a shore, paddling at a steady pace, while the shore sits on a raft that keeps drifting away faster and faster. At first, the swimmer gains ground, but once the raft's drift outpaces the swimmer's stroke, the shore recedes forever, and no amount of paddling will ever close the gap. Distant galaxies are that receding shore, and their light is the swimmer, forever chasing a coast that pulls away too fast. There is a strange sadness in it. Light is the fastest thing in existence, and even it can be defeated, outrun by the swelling of space across vast enough distances. The very expansion that reddens and stretches the light eventually grows fierce enough to keep that light from ever arriving at all. So, light can be beaten by the stretching of empty space. It can also be bent, twisted, and even trapped by something else entirely, by the crushing pull of gravity near the heaviest objects in the cosmos. A beam of light travels in a perfectly straight line until it passes near something massive enough to bend the very space it moves through. Gravity does more than pull objects down. It warps the shape of space itself. Anything with mass dents the space around it, and the heavier the object, the deeper the dent. A planet makes a small dent, a star makes a bigger one. A truly massive object makes a deep, steep well in the fabric of space. Now send a beam of light past one of these dents. The light still travels as straight as it can, but the space it moves through is curved, so its path curves along with it. The beam bends around the massive object, its route bent by the warp in space, like a ball rolling across a dented sheet and curving as it crosses the dip. Light that should have flown straight past instead swings around the heavy object, its direction quietly changed. This bending is real and measured. Astronomers watch it happen when the light from a distant galaxy passes near a massive object on its way to us. The light gets bent around that object, and the object acts like a giant lens in space, warping and magnifying the galaxy behind it. Sometimes the bending is strong enough to smear a single distant galaxy into arcs and rings of light, or even to split its image into several copies, all from one galaxy whose light took several bent paths around the massive lens. Scientists use this bending as a tool. A massive object in space becomes a natural magnifying glass, bending and focusing the light of far more distant galaxies behind it, letting telescopes see fainter and farther than they otherwise could. Some of the most distant galaxies ever found were caught only because a massive lens in front of them bent and brightened their ancient light on its way to us. Through all this bending, one thing holds firm. The light still carries its frozen clock. Curving around a massive object changes the light's direction, but it does not make the light age. The beam bends, swings around the deep well in space, and flies onward, still counting 0 time from its own side. Whether a beam travels straight or takes a long curved path around a heavy object, its own clock reads the same. It arrives fresh, however twisted its route. Picture rolling a marble across a stretched rubber sheet with a heavy ball resting in the middle, making a deep dip. The marble rolls straight until it nears the dip, then curves around it, its path bent by the sag in the sheet. The marble never slows its own inner sense of time. It simply follows the curved shape of the surface. Light does the same, tracing the bends and dips that mass carves into space. without ever aging along the way. So gravity can steer light, curving its path and even focusing it like a lens, all without touching the frozen clock the light carries. The beam bends but never ages, yet the deepest gravity wells in the universe do more than bend light gently. Near the most crushing objects in existence, gravity grows so fierce that it can grab light, slow its escape, and even wrap it into a perfect circle, trapping the fastest thing in the cosmos in an endless loop. Near the most crushing objects in the universe, gravity grows so overwhelming that it can catch a beam of light and bend it into a perfect circle. These objects are black holes, the collapsed remains of the most massive stars, packed so densely that they carve the deepest possible wells into the fabric of space. Their gravity is so ferocious that the dent they make is less like a gentle dip and more like a bottomless pit, plunging down beyond anything else in the cosmos. As a beam of light approaches a black hole, the bending we saw earlier grows extreme. Far away, the light barely curves. Closer in, the curve tightens sharply, the light swinging hard around the pit. And at one special distance, the bending becomes so precise that the light cannot pull away and cannot fall in. Instead, it wraps into a circle and orbits the black hole, going around and around in a ring, trapped in an endless loop. Scientists call this ring the photon sphere. It is a thin shell around the black hole where light can circle forever, or at least until the tiniest nudge sends it either spiraling in or flying off. Imagine a beam of light that leaves a distant star, sweeps in toward a black hole, and gets caught in this ring, circling the pit over and over instead of flying onward. The fastest thing in the universe, held in a loop by nothing but the crushing bend of space. Something wondrous happens for anyone who could stand near this ring and look along it. Light circling the black hole would carry images of things behind you, sending your own view around the loop and back to your eyes. You could, in principle, look sideways along the ring and see the back of your own head, lit by light that had traveled all the way around the black hole and returned. The bending of space would fold the view into a circle and hand it back to you. Through all of this, the light still carries its frozen clock, circling a black hole endlessly, wrapped into a ring by ferocious gravity. The light still counts 0 time from its own side. It does not grow old as it loops. It does not age in the ring. However many times it circles, its own clock reads the same as the instant it was born, because time along its path is stopped, whether that path is a straight line or an endless loop. Picture water swirling around a drain, caught in a tight circle just before it falls in, spinning around and around at the very edge. The photon sphere is like that edge, except it is made of light, and the drain is a black hole. Light circles the rim, held in place by the fierce inward pull of the pit, trapped between falling in and flying free. This ring of trapped light sits just outside the black hole's true point of no return. Circling light can still, with a nudge, escape and fly away to be seen. But a little deeper in lies a boundary far more absolute, a line past which even light, the fastest thing in all creation, can never break free again. That final boundary is where the story of light and time reaches its most extreme and haunting edge. Just inside the ring of circling light lies a boundary so absolute that once a beam of light crosses it, that light can never escape no matter what. Every black hole has this line drawn around it, an invisible edge marking the point of no return. Scientists call it the event horizon. Outside the horizon, light can still climb away from the black hole's pull, though the climb gets harder the closer in it starts. Right at the horizon, the pull grows so fierce that light barely holds its ground, and inside the horizon, the pull wins completely. Any light there is dragged inward, unable to fly back out, trapped forever inside the black hole. This is what makes a black hole black. Light that crosses the horizon can never come back to us, so no beam ever leaves to carry an image of the inside. We see the black hole as a perfect dark shape against the glowing sky, a hole in the light, because it swallows every beam that falls past its edge and returns nothing. The fastest thing in the universe, defeated and captured by the crushing bend of space, Think about how extreme that is. Light always travels at the full speed limit of the cosmos, born already flying at the ultimate pace, unable to slow down. Yet at the event horizon, the space itself is falling inward so fast that even light flying outward at full speed makes no headway. The light races upward with everything it has, and the space beneath it pours downward faster, so the beam is carried in despite its own best effort. It is running up a waterfall that flows down quicker than it can climb. And here is the piece that ties the whole journey together. Even trapped inside a black hole, dragged toward the center with no hope of escape, a beam of light still carries its frozen clock. From the light's own side, it still counts 0 time. It does not age as it falls in. Whether a beam flies free across open space for billions of years, or circles a black hole in an endless ring, or plunges past the horizon into the dark, its own clock reads exactly 0 the entire way. Time along the path of light is stopped, everywhere, always, even at the most crushing edge in the cosmos. Picture a fish swimming with all its strength up a river toward a great waterfall. Far downstream, the current is gentle, and the fish makes easy progress. Closer to the falls, the water rushes faster, and the fish struggles to hold its place. Right at the lip, the current exactly matches the fish's fiercest swimming, and it hangs there, going nowhere. Past the lip, the water pours down faster than any fish could swim, and it is swept over the edge. The event horizon is that lip, and light is the swimmer, unable to climb a torrent of falling space. So light can be reddened by the stretching cosmos, bent by gravity, trapped in a ring, and finally captured forever past the horizon of a black hole. Through every one of these fates, its own clock never moves. It never ages, whether it flies free or falls into darkness, which forces the strangest question this whole journey has been building toward. If light never experiences time, in any situation, anywhere in the universe, then what is time really? And is it as solid and real as it feels? If a beam of light never experiences a single second, anywhere, ever, then a deep question rises up. What is time really, and why do only some things feel it? Look back at the whole journey. Anything with mass moves through time, ticking along, aging, growing old. The slower it moves through space, the more steadily its clock runs. Speed it up, and its clock slows. Push it toward the speed of light, and its clock nearly stops. And light itself, with no mass at all, sits at the far end of that scale. Its clock stopped completely, feeling no time whatsoever. That pattern hints at something strange about the nature of time. Time is not a single steady drumbeat pounding the same everywhere for everyone. It flows at different rates for different things, depending on how they move. And for light, it does not flow at all. So time seems to be less like a fixed river running through the whole universe, and more like something each object carries with it, a personal rate that depends on how fast that object travels through space. There is a beautiful idea hiding here. Everything in the universe is always moving through a blend of space and time together. Sit still in space, and you plow forward through time at the full, normal rate, aging steadily. Start moving fast through space, and some of that motion gets traded away from your journey through time, so your clock slows. Push all the way to the speed of light, using up every bit of your motion on the journey through space, and you have nothing left over for the journey through time. Your clock stops. That is exactly where light lives, spending all its motion on crossing space and none on aging. So light and heavy matter sit at opposite ends of one scale. You, made of mass, move slowly through space and swiftly through time, aging with every heartbeat. Light moves at the ultimate speed through space, and not at all through time, forever frozen at 0. Everything else in the universe falls somewhere between those two ends, trading motion through space for motion through time. This suggests that the steady march of time you feel, the reliable ticking of your life, is tied directly to the fact that you carry mass and move slowly through space. Time feels solid and constant to you because you barely move compared to light. If you could somehow ride at the speed of light, that steady march would stop entirely, and there would be no passage of time to feel at all. Picture a wide field where everyone can only walk at the same total pace, but they choose their direction, walk straight north, and you make full progress northward. Turn to walk east, and your northward progress shrinks, because you have turned your steps sideways. Turn fully east, and your northward progress drops to zero, all your steps spent going crosswise. North is time, east is space. You walk mostly north, aging fast. Light walks fully east, aging not at all. This reframes time as something woven together with space, shared out differently among fast and slow things, stopped entirely for the fastest thing there is. Time, it seems, is something mass feels, and light is exempt, which lands us on the final, personal truth of this whole voyage, the quiet difference between you and the light streaming past you every second of your life. Here, at the end of the journey, sits a simple and staggering truth about you and about light. Two travelers crossing the same universe in completely opposite ways. You move through the cosmos by crawling through every single second. Your clock ticks steadily, one moment after another, carrying you from birth toward old age at the patient, unstoppable rate that mass demands. You feel every year. You gather memories, grow, change, and age because time flows through you without pause. That steady flow is the price and the gift of being made of matter, of moving slowly through space and swiftly through time. Light travels the exact opposite way. It skips time completely. A beam of light crosses the entire universe, billions of miles beyond miles, and spends not 1 second doing it. From its own side, it is born, and it arrives in the same instant, ageless and unchanged, however vast the distance. It never grows old, never gathers a past, never feels a single moment pass. That frozen stillness is the price and the gift of being massless, of moving at the ultimate speed through space and not at all through time. So the same universe holds two utterly different kinds of travelers. Slow, heavy things, like you, feeling every second, aging steadily across a lifetime. And light, the fastest thing there is, skipping every second, forever fresh, forever young. You crawl through time. Light leaps over it. Both of you cross the same cosmos, in the same instant of history, living in two completely different relationships with time itself. Think about what that means for the starlight landing in your eye tonight. Some of it left its home before the dinosaurs, and it arrives as fresh as the day it was born, having felt none of those ages pass. You, catching that light, have aged with every year of your life, feeling time flow steadily the whole way. In the meeting of your eye and that ancient beam, two travelers touch, one who felt every second and one who felt none at all. There is a quiet wonder in it. You are made to experience time, to live inside its steady current, to carry a past and move toward a future. Light is made to escape time entirely, to cross all of creation in a single frozen instant. Neither one is doing anything strange or broken. Each is simply obeying the deep rules woven into the universe, the rules that tie the passage of time to mass, motion, and the ultimate speed limit of reality. Picture two travelers setting out across a vast desert. One walks on foot, feeling every step, every sunrise and sunset, arriving weathered and older on the far side. The other travels in a single blink, crossing the whole desert without experiencing the journey at all, arriving exactly as they left. You are the walker, light is the blink. Same desert, same crossing, two entirely different experiences of the road. So the next time sunlight warms your face, or an ancient star pricks the night sky, remember what you are truly seeing: a traveler that crossed unimaginable distances and skipped every moment of the trip, arriving new after a voyage that would exhaust everything else in existence. Light never gets older, even across the whole universe, because for light, the whole universe is a single, ageless instant, and you, feeling every second, are the rare kind of traveler who gets to notice the miracle at all. You crawl through time while light skips it, And behind that difference sits a rule far bigger than light itself. The universe has a top speed, the same limit we have circled this whole journey. Light rides right at that limit. But the limit was never really about light. It is the speed of cause and effect. It is the fastest that any push, any signal, any influence of any kind can travel from one place to another. Nothing that carries news, nothing that makes something else happen, can move faster than that line. Light just happens to hit the limit because it has no weight. Anything massless is forced to the top speed, so light became the messenger we notice. But the rule underneath governs everything, not only light. Think back to the Sunday. If it vanished this instant, its light would keep warming your face for 8 more minutes before darkness arrived. Here is the deeper part. Its gravity would also keep holding the Earth in orbit for those same 8 minutes. The news that the sun was gone, both the light and the pull, would travel to us at the exact same speed and arrive together. For 8 full minutes, Earth would circle a sun that no longer existed, feeling a grip from something already gone. That is the speed of cause and effect at work. No event anywhere can reach out and change anything else instantly across distance. Every influence has to travel, and none of it can outrun the cosmic limit. The farther apart two things are, the longer before one can ever touch the other. Picture a kingdom where the only way to send any message is a single royal courier, and no courier is allowed to ride faster than one fixed pace. A command from the castle cannot reach a distant village any quicker than that courier can gallop. The farther the village, the longer before the castle's decision changes anything there. The universe runs on the same law, with the courier's top speed set at the speed of light. The delays are enormous. The sun's influence takes 8 minutes to reach us. The nearest neighboring star's influence takes over 4 years. A galaxy far across the cosmos cannot affect us for millions of years, because nothing it does can cross the gulf any faster than light. Every corner of the universe is sealed off from every other by this built-in delay, connected only by signals crawling along at the cosmic speed limit. So the reason light never ages, and the reason nothing can outrun it, come from the same deep source. The limit is baked into how cause and effect flow through space and time. Light simply shows us the limit in its purest form, a massless messenger pinned to the top speed forever. There is something almost lonely woven into this. No two distant places can ever share a truly instant connection. Everything reaches everything else late, delayed by the crawl of light across the vast dark. The universe is stitched together by messages that always arrive after the fact, never in the same breath as the event that sent them. And that raises a question stranger than any so far. If no signal can ever cross the universe instantly, if every influence arrives late, then the simple idea of a single shared moment, one universal now ticking everywhere at once, begins to come apart in your hands. Ask what is happening right now on a galaxy far across the universe, and you run into a shock. The question has no single answer. You feel like there is one universal now, a single present moment ticking everywhere at the same time. It seems obvious. Whatever is happening here this instant, surely something is also happening on a distant world, this same instant, sharing the exact same now. That comforting picture turns out to be an illusion. The trouble grows straight out of the last chapter. No signal can cross space instantly. Everything arrives late, so there is no way for two far apart places to ever check whether their clocks agree at the same moment, because any check has to travel at the crawl of light. And once you follow that carefully, something bizarre appears. Two people moving differently through space can honestly disagree about whether two faraway events happened at the same time. One observer says 2 distant flashes went off together in the same instant. Another observer, gliding past at high speed, says one flash clearly came before the other, and neither one is wrong. There is no master clock in the universe to settle the argument. Each observer slices up time in their own way, and their slices tilt differently depending on how they move. The idea of a single now, shared by everyone everywhere, simply dissolves. For places close together, moving slowly, the disagreement is far too tiny to notice. Your now and your neighbors now line up so closely that no one ever spots a difference. Stretch across the vast gulfs of space, though, and the cracks open wide. For a galaxy millions of miles beyond miles away, the question of what is happening there at this exact moment has no clean answer at all. Different observers would point to completely different events and each call it now. Light is the one solid thread connecting these distant places, and light always takes time to cross. So the only honest link we have to a faraway galaxy is old light, a message from its past, delivered late. We never touch its present. We only ever receive its history, carried to us fresh, but always aged, by our clocks, on the journey. Picture two towns that can only learn about each other through newspapers, and the newspapers travel at different speeds depending on who carries them. One reader gets today's edition, another gets a copy delivered slower, so they read different days and each calls their own copy the latest news. There is no shared today that both towns agree on, only papers arriving at their own paces. The universe works the same way, with light as the paper, and now as a headline no two distant places can ever share. This is one of the strangest gifts of understanding light. It strips away the comforting idea of a single cosmic clock ticking for all of creation, time, and now bend and tilt, shared out differently across the sprawling dark, held together only by signals crawling at the speed of light. The present you feel so surely is your present, sliced your way, and it does not stretch cleanly across the whole universe. Through all of this, light itself feels nothing, riding its frozen clock across every twisted slice of time. And light, it turns out, is not the only thing that races at the cosmic limit and skips time entirely. Something else rides right beside it, born from the most violent events in the cosmos. When two black holes crash into each other, they shake the fabric of space so hard that ripples race outward across the universe, riding at the exact speed of light. These ripples are called gravitational waves, and they are waves in space itself, stretching and squeezing everything they pass through as they spread. They are set off by the most violent events in the cosmos, like two black holes spiraling together and slamming into one, an event so powerful it briefly outshines all the stars in every galaxy combined, not in light, but in these ripples of shaking space. Here is the beautiful part. Gravitational waves travel at exactly the cosmic speed limit, the same top speed as light, and that means they carry the same frozen clock. They cross the entire universe, feeling no time at all, ageless, arriving fresh after journeys of billions of years, just like light. Light is not the only timeless messenger. These ripples in space ride right beside it, born in violence, skipping every second of the trip. Catching them is one of the hardest things humans have ever done. When a gravitational wave washes over the Earth, it stretches and squeezes everything, but by an amount almost too small to imagine, a change far tinier than the width of a single atom. Scientists built detectors miles long, precise enough to feel that faint shudder, and they have caught the ripples from black holes crashing together far across the cosmos, a whisper of shaking space, arriving unaged from an ancient collision. Now, for a lovely contrast, not everything that races across the universe skips time completely. There are tiny ghost particles called neutrinos, born in the hearts of stars and in violent cosmic blasts. Neutrinos have the faintest whisper of weight, just a trace of mass, so they cannot quite reach the cosmic limit. They race along at almost the speed of light, breathtakingly close, but a hair below. And because they fall just short of the top speed, their clocks are not fully frozen. Neutrinos do feel time, though only the barest sliver of it, aging by a whisper where light ages not at all. Neutrinos are wildly abundant and almost impossible to catch. Right now, billions of them from the sun are streaming through your thumbnail every single second, passing clean through your body, through the whole Earth, without touching a thing. They are the shyest particles we know, ghosts that ignore almost everything in their path. Picture a race with three kinds of runners. Light and gravitational waves are the perfect sprinters, forever at full speed, never aging a heartbeat, no matter how far they run. Neutrinos are the almost perfect sprinters, racing just a step slower, aging by the tiniest sliver across the whole journey. And everything with real weight, including you, jogs far behind, feeling every second of the road. So the universe sends its messages across the dark in several forms. Light, gravitational waves, and neutrinos all come racing in, the first two ageless at the top speed, the third aging by only a breath. Together, they let us hear the cosmos in more than one voice, catching events that light alone might hide. Gravity, though, does more than shake out ripples in space. It can reach into a beam of light directly, grab it, drain it, and even freeze it in place at the edge of the darkest objects in existence. Gravity can reach right into a beam of light, wring the energy out of it, and stretch it redder the harder it has to climb. We saw the expanding universe stretch light toward red as space swelled beneath it. Gravity does its own version of this, by a completely different route. When light climbs away from a heavy object, fighting up out of the dent that object carves into space, the climb costs it. The light loses energy on the way up, and losing energy stretches its waves longer, sliding its color toward red. The steeper the climb, the deeper the reddening. Light escaping a heavy star arrives a touch redder than it left, drained by the effort of pulling away. Near a black hole, this turns extreme. A black hole carves the deepest possible pit into space, so light trying to climb out of it loses enormous energy, reddening more and more the closer to the edge it starts. And right at the black hole's boundary, the point of no return, the effect runs all the way to its limit. Light struggling to escape from the very edge is stretched so far, so completely, that it reddens toward invisibility. Now, watch something fall into a black hole from a safe distance far away, and you see one of the eeriest sights in all of physics. As the object drops toward the edge, the light it sends back to you stretches redder and redder, and it appears to slow down. Closer to the boundary, it seems to crawl, its light dimming and reddening, until right at the edge, it appears to freeze. From your distant view, the falling object never quite crosses the boundary. It hangs there, frozen at the edge, its final light stretched so long and faint that it fades from sight, seeming to stop forever at the brink. Yet from the falling object's own side, nothing dramatic happens at the edge at all. It sails straight across the boundary and inward, feeling no pause, no freeze. Two views of the same fall, and both are true. The distant watcher sees an eternal freeze. The traveler feels a smooth plunge. The universe hands them completely different stories about the same event, and through every bit of this, the light itself still carries its frozen clock. Climbing out of a gravity well, reddened and drained, or hanging frozen at a black hole's edge as seen from afar, the light counts 0 time from its own side. It never ages, whether it escapes into the sky or freezes at the brink of the dark. Picture watching a friend walk into a thick bank of fog that grows heavier with every step. Their wave slows, their shape reddens and dims, and just as they reach the deepest part, they seem to hang frozen at the wall, fading from view, never quite seen to pass through. To you, they freeze at the edge forever. To them, they simply keep walking. That frozen figure in the fog is light at the boundary of a black hole, stretched and stalled by the fiercest gravity in the cosmos. So across every strange fate we have followed, reddened by the swelling universe, bent by gravity, trapped in a ring, frozen at a black hole's edge, or plunged into the dark, light has held to one unbroken truth: its own clock never moves. And that single unbroken fact, holding firm through every corner of the cosmos, points straight at the deepest reason we are able to know the universe at all. Every beam of light arriving on Earth right now is a letter from the past, delivered fresh, and together they hand us the entire story of the universe. Follow the thread through this whole journey, and it ties into one truth. Light rides the cosmic speed limit, so it carries a frozen clock, so it never ages, no matter how far it travels or what happens on the way. That single fact is the reason the sky is a machine for reading the past. Because light does not grow old, every scene it captures arrives in perfect condition, exactly as it looked when the light departed, however long ago that was. So look at what light gives us. The sunlight from 8 minutes back, the starlight from before the dinosaurs, the reddened glimmer of the first galaxies, blazing to life near the dawn of everything. The oldest glow of all, the leftover shine of the newborn cosmos, still washing over the earth from every direction. Each of these is delivered fresh, unaged, a flawless snapshot of a moment that passed away long ago by our clocks. The whole history of the universe is written in the light landing right now, waiting to be read. And someone has to read it. That someone is you, and every creature made of mass like you. You crawl through time, feeling every second, aging with every year. That steady march through time is exactly what lets you sit still long enough to catch these ancient messages and understand them. Light does the traveling, ageless and swift. You do the noticing, slow and aware. The two of you meet in a single glance at the night sky. One messenger who felt no time, one reader who felt it all. There is a quiet kind of wonder in that meeting. The fastest thing in existence crosses unimaginable distances and skips every moment of the trip. The slowest kind of traveler, made of matter, moves at a crawl and gets to witness the miracle. Light carries the story. You are the one who gets to learn it. Neither could do the other's job. Light cannot pause to understand. You cannot fly across the cosmos ageless. Between you, the universe becomes knowable. Picture a vast library filled with letters from every corner of history, each one somehow arriving with the ink still wet. No matter how long ago it was written, the letters cannot read themselves. They simply arrive, perfect and patient, waiting. And you walk in, slow and mortal and curious, and you open them one by one, learning the whole story of everything from messages that never aged a day. Light writes and delivers the letters. You are the reader who finally opens them. So, the next time warmth from the sun lands on your face, or an ancient star pricks the dark overhead, remember what is truly happening. A messenger that crossed a gulf beyond imagining, skipping every second of the trip, is handing you a perfect picture of a moment long gone, fresh as the instant it was born. Light never gets older, even across the whole universe. And that is the exact reason you can look up and see the beginning of everything, laid out fresh above your head. You are the slow traveler who feels every second. And because of that, you are the one who gets to catch the ageless light and finally understand the story it has carried all this way.